So let's do another example of sampling and reconstruction to solidify the concepts of sampling, measuring a signal at periodic intervals of time, aliasing, the problem that happens when we do not sample fast enough, meaning when we undersample, or when the sampling frequency is less than twice the maximum frequency, and the importance of the pre-filter, also known as the anti-aliasing filter. So we have a signal, x of t, and then the first item is determine the minimum sampling frequency that will not cause aliasing. Okay, so our signal is 5 plus 3 cosine. Since we're going to be working with frequency in hertz, I'm going to put all this in hertz. So this will be 2 pi. To get the pi up, the frequency in hertz is 0.5 hertz t, so that's the first component, plus 2 cosine of 2 pi times 1t plus 1 cosine of 2 pi 1.5 t. Right? And so minimum sample frequency that will not cause aliasing. Remember the problem of aliasing, where we are not going to be able to reconstruct. So for that we need to meet the sampling theorem. Fs needs to be greater or equal than 2 Fmax. What is our maximum frequency in this case? Is 1.5. Oh, sorry, this was in milliseconds. So these are all kilohertz. Okay, so this is 2 times 1.5 kilohertz or 3 kilohertz. Meaning, if we sample at 3 kilohertz, the samples of x of t sample at nts where, remember, n is just the integer 0, 1, 2, 3, 4, 5, gives you the order of the sample, and this ts is 1 over 3k. From the samples that we get, we will be able to reconstruct x of t exactly, meaning we do not lose any information. So that's the good scenario. But then in B, assume that actually Fs is 1.5 kilohertz. When we needed, recall, we needed 3 kilohertz. What happens in that situation? Well, we are undersampling, we are not meeting the requirements of the sampling theorem, therefore we're going to have problems. What is the problem? We're going to have aliasing. And so what we have here in B, it says, assume that this is sampled at 1.5 kilohertz and then immediately reconstructed with the ideal analog reconstructor to produce the analog signal XA. Okay? Let's see what happens in the situation where you do not have a pre-filter and when you have a pre-filter. Okay, so let's see. Let's see what happens with the aliasing. So there are some components that even if we undersample here at 1.5 kilohertz, we are going to be fine. Namely, this is at 0 kilohertz, 0 hertz, no problem, that will not have a problem. And this is at 0.5 kilohertz, that will not be a problem. This, however, we will have a problem, and in this we will have a problem. Let's see that. The original frequency that we have, this 5, is 0 hertz, and that's our frequency alias is going to still be 0, no problem. Our frequency 2 was 0.5 kilohertz, and it is still going to go through, because remember the Nyquist range here, if we sample at 0.5 kilohertz, it is 0.5 over 2, meaning it's between minus 0.75 kilohertz and 0.75 kilohertz, right? So this is within that range. And so, fine, 0.5 kilohertz. But the third component here, we have a 1 kilohertz that is going to be outside the 0.75 range, or the minus 0.75 to 0.75. And so we're going to have an alias. How do we determine the alias? You pick the frequency that you have, 1 kilohertz, and then, because we have spectral replicates at the sampling frequency, you have this, you can say plus minus multiples, I'm going to say m, times the sampling frequency, fs, m times fs, which in this case is 1.5 kilohertz, 1.5. And the one that is going to be alias is the one that is within minus 0.75 and 0.75. And so you can plug values of n equals 0, 1, 2, 0, minus 1, minus 2, and see which one falls in the Nyquist range. This is called the Nyquist range. And so we can see here that if we do m equals minus 1, we get 1 minus 1.5, it gives me here minus 0.5 kilohertz. So this 1 kilohertz is going to alias to minus 0.5 kilohertz. Notice that if we did m equals 0, 0 times 1.5 gives me 0, so I have 1 outside the range, will not work. M equal 2, it will be 2 times 1.53 plus 1, 4 outside. N equals minus 1 is what we have here. 1 minus 1.5 gives me the minus 0.5, which is within the range. So that's actually the alias component. And we have one last frequency, which is 1.5 F4A, and that's 1.5 plus minus m 1.5. If m is equal to 1, we have 1.5 minus 1.5, 0. And that's within that range, and it's the only one that's within the range. And so let's see what we reconstruct if we do not use the prefilter. If we didn't have a prefilter, if we didn't band limit the signal, and we still sample at 1.5 kilohertz, meaning we did not meet the sampling theorem, what we get? No prefilter. You get the analog signal that you reconstruct is, okay, this component, 5.5 plus this component, the one here, cosine of 2 pi 0.5t. Fine, it went through, but the third and the fourth component are going to give us problems, because not only they are going to alias, and so you're going to lose those, but they are going to distort the other components that could have gone through had we used a prefilter. Let's check it out. 2 times cosine of 2 pi. Now, instead of being a 1 kilohertz, is going to be this minus 0.5 times t, plus the last one is going to be 1 cosine of 2 pi instead of being 1.5 kilohertz, is going to be times 0 kilohertz. And so let's work this out. This is equal to 0, is equal to cosine of 2 pi 0 t, cosine of 0 is 1, and so we are going to, this is going to be equal to 1. And in this case, cosine of 2 pi minus 0.5 is equal to cosine of 2 pi plus 0.5, right? The cosine has that symmetry. And so this component is going to add with this, and this component is going to add with this, meaning 5 plus 1 gives me 6, and then 3 plus 2 gives me 5 cosine of 2 pi 0.5 t. So this is what happens with our prefilter. This is what we will reconstruct. Notice we are not reconstructing the original signal. Okay? We are not reconstructing this. But notice that we are also not even reconstructing the lower components. 5 now is 6, and 3 pi t becomes 5 there. So even the components that could have gone through get distorted by those for which we did not meet the sampling theorem. So what could we have done if the maximum frequency that we could use due to hardware limitations is 1.5 kilohertz, and this is the signal that we have? Well, it is better to prefilter. If you prefilter, what you are doing is cutting this component and this component, meaning any component that will alias anything above half the sampling frequency, anything above that 0.75, you eliminate it. You use an analog filter, a pre-filter, or an anti-imaging filter to eliminate, an anti-aliasing filter to eliminate the alias component. So you eliminate this alias and this alias by cutting this component and this component. Because if you do not cut them, they distort even the components that you could have captured at a sampling frequency. And so what will you reconstruct then? Well, if you cut these components with a low-pass filter, with a pre-filter, with the anti-aliasing filtering, you just reconstruct 5 plus 3 cosine of 2 pi 0.5 t. Because you are not having aliasing signals, like you have here, these two, that distort back, like this 0.5 is going to distort this one, and this other one is going to distort this one. So if you're in a situation, if you're ever in a situation that because of your hardware, you have a maximum frequency that you can do, like in this case, imagine that it's 1.5 kilohertz, and you know that you have higher frequency components in your signal, you need to get rid of those prior to the analog to digital conversion. And that's taken care of with the pre-filter or the anti-aliasing filter to eliminate these alias components, because otherwise, again, I'm repeating myself, otherwise, not only you will not get those higher components, you get something else, you will get aliasing, but those alias components, they will corrupt the spectrum that you could have gotten in the range that is appropriate. Okay? In what's going on here, if we were to plot the spectrum, is that we have the spectral lines at 0, at 0.5, and minus 0.5, at 1, and minus 1, at 1.5, and minus 1.5. Okay, and so you have 5, this will be 5, at this one it will be 3 over 2, and 3 over 2, 2 over 2, 1, 1 at 1, and 1 half, 1 half. This spectrum is going to repeat at the sampling frequency. If you sample at 3 kilohertz, fine, no problem. But if you sample less than that, like if you sample at 1.5, this is what happened in this case. This was the sampling frequency, and so effectively when we sample at 1.5, what we have is that, okay, this and the 0 component went through and the 0.5 component went through, what you see here. Okay? If we had used a low pass filter to cut everything else, no problem. But since we didn't do that, the 1.5 minus this one alias back in order to knock this one, and this one alias back to knock this one, this one, this one, and then you have the 1.5, sorry, the 1 alias back to knock this one and this one to increase it by 2 now, and the 1.5 the alias back to 0 and 0, those components. And so you ended up correcting this, 5 becoming 6, and the 3 added by an amplitude of 2, because those two add together. Okay, so let's recap. When you have a continuous time signal and you want to use digital signal processing, you are going to need to sample it and quantize it. In that process, prior to sampling, we are going to use a pre-filter, also known as an anti-aliasing filter, that's an analog filter, in order to band limit the signal, to give it a maximum frequency. In order to make sure that you always have fs greater than twice the maximum frequency. If you meet this, you can reconstruct the signal perfectly. If you are constrained by your sampling frequency, you still need to band limit, because otherwise you correct even the section of your signal that could have gone through. Thank you. Now, I recommend that in each of the problems that we saw, that you do a MATLAB simulation and you actually get to see the samples, etc. Now, we have not covered the process of quantization. We will cover it later in the course, and that's because going from continuous time to digital, the process of sampling, meaning converting the continuous time signal into the discrete time signal, is the one that theoretically requires more understanding. The other one, the quantization, this is simply you are going to have a finite set of intervals, so your sample fall here, well, it's going to be either this one or this one, simply because you have a finite number of bits. And so effectively what you are doing is, once you have a finite set of levels, once this is quantized, n number of bits, effectively not only you have made the time with discrete time an integer and belongs to C, but the amplitude, although you can have as much precision as you want, is now a countable set, so it's also an integer. That's why it's going to be great to be used with a processor. Now, when we do the discretization in time, there is all this theory about, well, the sampling theorem, how do you reconstruct the ideal reconstruction, what happens in the spectrum. For the quantization, the difference between the digital signal, I'm going to you have x of t, once we sample NTS for n belongs to C, we get an x of NTS where both x of t as well as x of NTS, both of them belong to, you have infinite precision. If they are real signals, belong to real numbers, or more general mathematically, they are in the set of complex numbers. Right? The next step, if you take this to x of NTS quantize, the difference between x of NTS minus x of the quantization there is just going to be some error that you can make as small as you want by increasing the number of quantization levels. So that's, you can think of that, oh, that's a small error that you have there that gets better and better the higher the number, the more quantization that you have. Okay, you increase the number of bits, and so for a particular application, the only thing that you need to be concerned is, well, what is that difference, and how much can you tolerate? Otherwise, just increase the number of levels, increase the number of bits. That's it. This is the reason, by the way, why we are going to develop all the DSP theory using discrete time signals, right? The difference between the discrete time signal and the digital is just that you quantize it. And so it's a small change, perhaps a small error. And remember that error, you can make it as small as you want by increasing the number of bits. Thank you.